So, what exactly are algorithms? Informally, an algorithm is just a set of steps used to solve a problem. In other words, it's a solution to a specific task. Let's take an example to make it clear. Consider finding the factorial of a number. We can describe an algorithm like this. So, this algorithm initializes a variable fact to 1. It then iterates through every value v in the range from 1 to n and multiplies the current value of fact by v. After the loop completes, the variable fact holds the factorial of the input number n. In essence, this code calculates the product of all positive integers from 1 to n, providing the factorial of n. Now, this algorithm is described in plain English. If we were write it in a programming language, we would call it a code instead. Here's the code for finding the factorial of a number in C++. This C++ code defines a function named factorial that takes a positive integer n as an argument and returns its factorial. Inside the function, an integer variable fact is initialized to 1. The function then uses a for loop to iterate through every value v from 1 to n inclusive. In each iteration, the value of fact is updated by multiplying it with the current value of v. Finally, the function returns the computed factorial stored in the variable fact. This function can be called with a positive integer as an argument to obtain the factorial of that number. Use of data structures and algorithms to make your code scalable. In the world of programming, data structures hold data, and algorithms are used to manipulate that data to solve different kinds of problems. You might be wondering why top companies place such a high emphasis on hiring programmers who excel at optimizing algorithms. Well, that's because data structures and algorithms play a crucial role in making your code efficient and scalable. Time is precious. Let's take a scenario to understand this better. Meet Alice and Bob, two programmers trying to find the sum of the first 10 raised to the power of 11 natural numbers. Bob comes up with this algorithm. So, this algorithm initializes a variable sum to 0 and then utilizes a loop to iterate through every natural number n in the range from 1 to 10 to the power of 11. In each iteration, the value of n is added to the current value of sum. After completing the loop, the variable sum holds the sum of all natural numbers from 1 to 10 raised to the power of 11. On the other hand, Alice implements the corresponding C++ code. This C++ code defines a function named findSum that calculates the sum of all natural numbers in the range from 1 to 10 raised to the power of 11. Inside the function, an integer variable sum is initialized to 0. The function uses a for loop to iterate through every value v from 1 to 10 raised to the power of 11 inclusive. In each iteration, the value of v is added to the current value of sum. Finally, the function returns the computed sum stored in the variable sum. This function can be called to obtain the sum of natural numbers in the specified range. Both Alice and Bob are excited about their solutions, but when they run the code, they encounter a problem. Bob's code is taking a significant amount of time to execute, and Alice wonders what's wrong. The time taken by a computer to run code depends on the number of instructions executed and the time to execute each instruction. In this case, the total number of instructions executed is 2 multiplied by 10 raised to the power of 11 and add 3 to it. Now, Assuming a computer can execute 108 instructions in 1 second, the time taken to run the code will be greater than 33 minutes. So, as you can see, Bob's algorithm is not optimized and it's taking more than 33 minutes to run. But we can do better. By using the formula for the sum of the first n natural numbers, which is n multiplied by n plus 1 and divided by 2, we can create a much more efficient algorithm. So, this code executes in just one instruction, no matter how large the value of n is. It's what we call a constant time algorithm. Using this optimized algorithm, the time taken to find the sum is 1 divided by y, which is just 10 nanoseconds. So, as you can see, choosing the right data structure and right algorithms can significantly impact the performance of your code, making it scalable and efficient. Scalability refers to the ability of an algorithm or system to handle larger problem sizes without requiring a significant increase in resources or time. Memory is another important fact to consider. While dealing with code that requires storing or processing a large amount of data, it's crucial to optimize memory usage. For instance, you can store just the date of birth of people instead of their age, calculating their age on the fly when needed. In this course, we will explore various data structures and algorithms and understand their efficiency in solving different problems. You will gain insights into evaluating the efficiency of an algorithm and learn to choose the best approach among several options. Scalability is a term you often come across in the world of computer science. It's a combination of scale and ability, representing the quality of an algorithm or system to handle larger and more complex problems. So, let's illustrate this concept with a simple analogy. Imagine we need to set up a classroom for 50 students. The solution is quite straightforward, right? We can book a room, get a blackboard, and a few chalks, and voila, the problem is solved. But what if the number of students increased to 200? Well, the same solution could still work, but it would require more resources, right? Perhaps we would need a larger room, like a theater, a projector screen, and a digital pen to accommodate the increased number of students. Now, let's take another step further. What if the number of students increased to 1000? The previous solution might not suffice anymore. It could either fail to handle such a large number of students or consume an enormous amount of resources, making it inefficient. In this case, we can say that the solution is not scalable. So, what makes a solution scalable? A scalable solution can handle problems of larger size without requiring a significant increase in resources or time. Now, let's relate this to the algorithms we discussed earlier. Remember our first solution to find the sum of the first n natural numbers? It wasn't scalable because it required linear growth in time with the linear growth in the size of the problem. So, such algorithms are known as linearly scalable algorithms. On the other hand, our second solution, which utilized the formula sum equals to n multiplied by n plus 1 and divided by 2, was very scalable. It didn't need any more time to solve the problem as the size of n increased, right? So, such algorithms are known as constant time algorithms. So, as you progress in this course, you will discover that optimizing algorithms for scalability is essential in building efficient software systems. But it's not just about time efficiency. Money efficiency also plays a crucial role. Memory is expensive in terms of computation. While dealing with code or systems that require storing or processing a large amount of data, it's critical to save memory whenever possible. One way to achieve this is by carefully designing data structures to store only the necessary information. For a good example, when storing data about people, you can save memory by storing only their date of birth instead of their age. Because you can always calculate their age on the fly using their date of birth and the current date. Let's take a look at some examples of how learning algorithms and data structures can enable you to achieve impressive efficiencies in solving various problems. Example 1. Age group problem. Suppose you need to find people of a certain age group. The naive algorithm that goes through all the persons one by one to check if they fall into the given age group is linearly scalable. On the other hand, the binary search algorithm claims itself to be logarithmically scalable. This means that if the size of the problem is squared, the time taken to solve it is only doubled. So, for a group of 1 million people, the binary search algorithm will take only 2 seconds to solve the problem, while the naive algorithm might take around 12 days. Example 2. Rubik's Cube problem. Imagine you are writing a program to find the solution to a Rubik's Cube. With a mind-boggling huge amount of positions, you might wonder if it's even possible to solve it efficiently. Thankfully, the graph algorithm known as Dijkstra's algorithm comes to the rescue. It allows you to solve this problem in linear time, meaning it allows you to reach the solved position in the minimum number of steps. Example 3. DNA problem. In the field of bioinformatics, you may be tasked with finding a specific pattern in a DNA strand. The simplest algorithm would take time proportional to the number of characters in the DNA strand multiplied by the number of characters in the pattern. However, using the KMP algorithm, you can significantly speed up the process. It takes time proportional to the number of characters in the DNA strand plus the number of characters in the pattern. This can make the algorithm much faster, even up to 1000 times in some cases. So, as you can see, learning algorithms and data structures empowers you with the ability to tackle complex problems efficiently and optimize your code for both time and memory.